Okay. Tomorrow, your bridge designs are due. All I really care about is trying to prevent you. There's lots of different designs that are successful. I'm just trying to get you to think prior to Sunday night, um, and also trying to prevent catastrophic design. Like, oh, that's gonna fail. Okay, so you're welcome to modify your designs, like what you show me. You're welcome to deviate from that. I'm fine with that. I just trying to prevent.
Is it going into lab grade or a test grade?
Oh, definitely lab.
Lab.
Yes. Okay. So I want to highlight a couple things on that. So tomorrow I'll just walk around and check your designs, just like homework. Okay. So there'll be an 8-inch gap. We'll set up the lab tables 8 inches apart from each other, and we'll test on that. Okay. So what we'll do is, actually, hold on a second. Here's how you're going to test your bridge. This block that I give you the dimensions for. This is going to rest on your bridge or in your bridge, depending on how you design it. There'll be a floor or a ceiling or something. This goes in the middle of your bridge. Okay. Somehow you need to be able to access this to take this hook and put it through this hole, and then put this nut on there. This is what rests on your bridge, and then we will take a bucket and support that. Or hang it from here. Load this up with sand until this fails. Okay. The minimum weight that you need to hold is this hook and wood block.
How heavy is that?
I don't know. 1/10 of a pound, maybe. Okay, but this is heavier than 2 strands of spaghetti can hold. So don't come in here thinking, check this out. Here's my bridge. 2 strands of spaghetti. Okay, it's not a bridge. Good with that? So I would recommend wherever this rests on, fortifying that, like making that strong. It really stinks when you test it and just this part busts out and you're left with an intact bridge, just a hole in the floor. Does that make sense? Okay. So that's how we're gonna test it. Again, some rules. You're just using spaghetti. Bucatini. This is not spaghetti. They might say extra thick spaghetti, but this is a different type of pasta. Piccoli, I don't know, I've never seen this. Well, it's kind of, if you think like, found some massive spaghetti, it's not spaghetti.
Spaghetti.
Just go get the cheapest spaghetti you can find. What's up, gentlemen?
What do you mean cheapest spaghetti?
Cheapest.
The best?
No, I don't want the healthiest. I want just cheap stock processed Walmart version spaghetti.
Oh, so this isn't This is real stuff.
The Great Value brand.
That's right. That's right.
So, Saturday, do we have any soccer guys in here? One, just one. I think you guys all know they're playing the soccer state championship. And the Indiana High School Athletic Association started something about 3 or 4 years ago where any team that plays in the state championship match, game, whatever it is, gets to honor a champion educator. And this year we are honoring Mr. Smiley as our champion educator from Harrison. He'll be recognized, hopefully he's available Saturday afternoon. But that's, I just found out yesterday, that project I was working on, you know.
Yeah. Interesting.
He'd been here 25 years and been teaching for 25 and all of them here. So I think he's very deserving of this honor. So let's have a little applause as our champion educator. Congratulations.
Thanks, sir.
Yeah.
There's everything. Oh, did
Well done,
you,
Mr. Smiley.
did you have your Thursday joke for him?
I do.
Tell him.
Albert Einstein was a wonderful man, but his brother Frank is a real monster.
Hey, does anybody in here know why the pumpkin didn't cross the road? Didn't have any guts.
That was awesome.
So, congratulations. I'll get you some more information, but it'll be halftime of our match.
Okay.
That starts at 4. And we'll take you out on the field and
Okay.
Congratulations.
do
Thank
some
you.
of this.
Yeah.
You know, and then watch us
I want to
win. There you go.
The lunch duty pushed you over the edge.
Yeah. Hey, and maybe we can get you in the hospitality room and you can have good spaghetti.
There you go.
Yeah.
Perfect.
All right.
Thank
Thanks
you,
for letting
gentlemen.
us interrupt.
No problem. Awesome. Okay. So, everybody good with, like, don't get creative on your spaghetti.
So, are we just trying to submit the designs or the whole thing entirely?
Tomorrow just the design, and Monday the whole thing entirely.
Like built?
Yeah, you're built, yeah, you're ready to get rock and roll on Monday. Okay? So, some quick things. You can't glue spaghetti parallel, but you can run them parallel. There just needs to be a spaghetti width gap between them. Okay? The note cards, you can have a 1/2 inch note card, half by 1/2 inch note card, so you're cutting it. You don't have to have the note card. That's just enabling your junctions to be stronger, so you can like put the glue there. It's not required. Okay? So,
I have that, but I have like 3 pieces coming together. Can I still do that?
oh yeah. Yeah, anytime you got pieces, like if you have a whole bunch. Yeah. Okay, now what you can't do is like break a whole bunch of things and then they go no card. Like, then that's a bridge of note cards and glue, not a bridge of spaghetti.
That would just put more stress.
Okay, so, you can do this for the floor, like
Grid.
layer it, but 3 layers max. I don't want a brick of spaghetti as your bridge.
So the floor base is a grid,
You can,
a
yeah,
flat grid.
yep. That's
That
one,
sounds so wrong,
okay,
genuinely so wrong.
good. Yeah, any other questions about the bridge design, construction? What you can and can't do? Any glue is accessible. Don't do Elmer's, white glue.
Sometimes it could be the strongest screws for spaghetti.
What happens if we do?
I mean, you gotta think of drying time too. Epoxy's the strongest, but that's nasty to work with.
Yeah.
So,
Which one's faster to dry and
I'll let you figure that out. Okay, any other questions? Okay. All right. Next, unit. Work and energy. All right. So, first up is kinetic energy. All right, kinetic energy. You might remember this from junior high physical science. Okay, this is the energy of motion. It's the energy of motion. The equation for that is 1/2 mass times speed squared. Okay. So this is speed, not velocity. This cursive, that's script V. Okay, and M is for mass. Okay, so does kinetic energy have direction? Mass doesn't have direction, speed doesn't have direction,
It's just how it exists.
does not have direction. Okay, so no, meaning it is a scalar measurement. Okay, no direction. Okay, the unit for kinetic energy is a joule. Symbolizes the capital J. And where that comes from, what's the unit for mass?
Kilograms.
Kilograms. Okay, what's the unit for speed? Meters per second, and we're squaring that. So meters squared over seconds squared. So that's how the primary units, the primary colors of units of SI units combine together to give you a joule. Okay? So if something is moving, it has kinetic energy. How much kinetic energy, you can figure that out by multiplying 1/2 times its mass times how fast it's moving squared. The squared is just applied to the speed. Good? All right. Work. The variable for work is a capital W. The equation for that is force parallel times the distance. So this little dude here is the component of force that is parallel to the direction of motion. Okay. And then D is for distance. Good with that? So, the unit for work comes from, what's the unit for force? Newtons. And what's the unit for distance? Meters. Newton times a meter is, cliffhanger. Let's break that down. What's a Newton equal to? And Newton comes from what's mass? Kilograms. What's acceleration? Meters per second squared. So this is equal to a kilogram meter per second squared times meters, which is equal to, we simplify that, kilograms meters squared over second squared. Does that look anything familiar? This is equal to also a joule. That's weird. So is work and energy the same thing? No, but they are related. Here's the idea. So, in science, you've been introduced to this idea of energy since like elementary school, right? Energy cannot be created or destroyed. Right? I mean, that's like, you get energy from the sun, and that turns into plant energy, and then a herbivore eats it, and it becomes food energy. And then a carnivore eats it, and it becomes more different food, meat energy. And then we eat it, like this energy cycle, right? Like this whole, like you've been studying this forever, okay? So far in physics, we haven't talked about energy. We've talked a lot about forces. So the question is, how does force affect energy? To answer that question, we have baked up this measurement called work that relates force and energy, how force affects energy. You okay with that? Yeah. So that's why they're both in joules. Yeah. So, that's some foreshadowing there. Based upon this equation, that I'm going to have to rewrite, when would work equal 0? Go ahead and tell your neighbor. When would work equal 0?
When they're both done with here.
Correct answer. Okay, when is When would work be equal to 0? Okay, when distance, so if distance is equal to 0. Okay, so this I didn't do any work. That makes sense? Might exert force. If I don't move anything, no work is done. Okay? What else? Okay? So if there's no force, so the follow-up question is it possible for a force to be acting on an object and the object move, yet it does no work? Is that a possibility? Is it possible for a force to act on an object, the object moves, but no part of that force is parallel? What do we call that if the force isn't parallel? There's no part of that that is parallel. We would say that the force is perpendicular. So if the force is acting perpendicular to the direction of motion, how are we doing with that? Yeah. So in order to do work, you have to have a component of force that's acting parallel to direction of motion and the object is moving. Good? Neighbor? Correct answer is no. Not doing work, okay? So, this process here, doing work. This, just holding it, I'm exerting force, is a good workout. But from a physics point of view, just suspending this, no work, okay?
How do you know if the force is parallel or perpendicular? Like,
Good question. I think this example will bring some illumination. You might need a calculator. Tell your neighbor what you got.
Wow.
Yep.
All right.
Okay, so your free body diagram. Looks like this. Yes? Okay, so all the stuff you've learned so far is still valid and true, still useful. Okay, now, is all of tension going parallel to the direction of motion? No. Which component is going parallel to the direction of motion? FTX is going parallel. Okay, so the work done by tension would be equal to FTX times the distance. Okay, so your FTX at 600, 60 degrees, FTX cosine 60 is equal to FTX over 600. FTX ends up being 300 newtons times 20 meters. The answer is C. 6,000 joules. Good?
So you don't need friction at all, sorry.
Great question. No. So I'm asking just for what is the work done by tension.
Okay.
Okay? So if I specify a force, that's all I want you to worry about. Okay?
Well, what about the friction?
Yeah. Hang on to that. We'll circle back around. Everybody good with that?
Yeah.
Okay. All right. When is work positive? Work is positive when the force parallel acts in the same direction as the motion. And when it's negative is when the force acts in the opposite direction of motion. So if the force is acting in the same direction, the way it's moving, positive work, if it's acting in the opposite direction, then it is negative work. Good? Okay.
When you say the force parallel, what is it parallel to? What?
Good question. Parallel to distance. So if you're moving this way, your FTX is parallel to the distance. Good question. Okay. All right, so is work a scalar or a vector? So this is crazy. It's actually a scalar. You're like, what? It has positive and negative. First time. Measurement in physics, the positive and negative does not communicate direction. That seems stupid. So when it is positive, this means, and we're going to make connections with energy here. You have, if a force is doing positive work, then this means the force is contributing to the kinetic energy of the object. Okay, if you're doing positive work, it's like, yeah, come on, let's give us some kinetic energy here. Versus if it's negative work, the force is taking away kinetic energy from the object. So positive or negative work communicates if the force is a giver or a taker. If it's giving energy, it's like, yeah, positive work. If it's taker, like, oh man, negative work is being done. Proud of that. Okay. Well. Tell your neighbor. Tell them why.
Applied force.
I thought it was like before this, so that's why I was thinking
How would you know? What you
Okay, how many forces are acting on the object? 4. Which of those is not doing work? Normal force. Why? The direction of motion is down the ramp. But the normal force is acting perpendicular to the way it's moving. Not doing work. Correct answer is 3 forces are doing work. 4 forces are acting on it, but only 3 are doing work. So you need to make a distinction between acting, which is straight up free body diagram stuff, and then doing work. You need, it's another condition, a secondary, an additional condition, like it needs to, some part of that needs to be parallel to the direction of motion. Okay? So which forces in this example are doing negative work? Tell your neighbor. Okay. You're pushing it up the ramp, but it's sliding down, and friction is also going in the opposite direction of motion. 2 forces. Friction and applied force are doing negative work. And what is the single force doing positive work? Gravity. Is all of gravity doing work? Just, so gravity is going straight down. You tilt your axis, and it's just Your FGX is doing positive work. Is acting
What about the normal force?
parallel to the direction of motion, the same direction of motion. Normal force is acting perpendicular to the direction of motion. It exists, but it does no work. Good? Okay. Coming back to dragging our box here. Tell your neighbor. Tell them how you got there. Correct answer is? Is everybody good with B? Okay. Friction is acting parallel to the direction of motion,
The one in class, like,
all of it, times the distance. And it's acting in the opposite direction of motion, so that's why it's negative. Yes? You okay with that? Okay. So, how much work is gravity doing? Tell your neighbor. Tell them why. Correct answer is 0. Why? It's acting perpendicular to the direction of motion. Okay. So what is the net or the total work done by all the forces in this scenario? Yep, hold on to it. Tell your neighbor.
Out.
Okay, so the net work would be equal to the 6,000 joules of work done by FTX plus the negative 4,000 joules of work done by friction. Gravity did no work, normal force did no work. Okay? So that would be the net or total work. With that? So, I'll leave you with this. Net work, you can find it either by adding up the work done by all the individual forces. And that's what we just did. The other way to do it, which is equally valid, is to say the net force that is parallel to the direction of motion times the distance. Okay? Here, for this example of dragging the box, that would look like this. you'd have FTX minus friction times your distance. Okay, so this was 300 newtons minus 200 newtons times 20 meters. So 100 times 20 gives you 2,000 joules. That's exactly what we had here. Good? Okay, bridge design is due tomorrow.